Today we're breaking down the Youtu-VL technical report from the team at Tencent's Youtu Lab. And this paper is, well, it's proposing a pretty massive shift for vision language models.
It really is. They're going after a core problem in almost every major VLM today, something they call text-dominant optimization bias.
Right. The idea that current models, think LLVA, even the GPT-4v variants, treat images as these passive inputs. They really only care about generating the right text.
And in doing so, they lose all this fine-grained visual detail. It creates a huge information bottleneck. So the Youtu-VL team is basically flipping the whole paradigm on its head.
With this new approach, VLUAS.
VLUAS, Vision Language Unified Autoregressive Supervision. The whole idea is moving from vision as input to vision as target.
So the model isn't just predicting the next word, it's actually being forced to predict the image itself, almost like it's speaking a visual language.
Exactly. And by doing that, they've built a single standard transformer architecture that can do general multimodal tasks and heavy-duty vision stuff like segmentation or depth estimation.
All without needing extra decoders or specialized heads.
No more stacking a SAM decoder on your LLM. It's one model, one vocabulary for both text and pixels.
Welcome to AI Paper Podcasts, where we summarize the latest AI and tech papers for the technical community. I'm your host.
And I'm your expert co-host. So let's get into the details of Youtu-VL.
Okay, so let's start with that term you mentioned, text-dominant optimization bias. It sounds like the villain of this story. I mean, VLMs are already pretty good at describing images, so what's actually breaking?
It all comes down to the loss function. I mean, think about how we train a standard VLM, like a LLVA or a Quinn. You've got a visual encoder, maybe a CLIP or a SIGLIP.
Right, it crunches the image into features.
Exactly. Then it goes through a projector and into an LLM. And that LLM is only trained to do one thing, output text.
The classic P of text given image.
The probability of the text based on the image. Right. And so the supervision signal, the gradients that update all the weights in the network, they come entirely from getting that text right. If the correct caption is a dog on a rug, the model only needs to recognize the features that trigger the words dog and rug.
So if the rug has some intricate pattern or the dog's collar has a specific texture,
the model is actually incentivized to ignore it. That information doesn't help it minimize the text loss, so it gets thrown away. That's the bias. The model gets, lazy with visual details because it's only viewing the image through this narrow lens of what's needed for a caption.
That's a great way to put it. It's like skimming a textbook just to answer the questions at the end of the chapter. You're not actually reading the prose, you're just pattern matching for the answers.
That is a perfect analogy. And the result is what the paper calls coarse-grained multimodal comprehension. The model gets the gist, but it fails at dense perception.
So if you then turn around and ask that same model to, say, segment dog, identify every single pixel that belongs to the dog, it can't do it.
It struggles because it never learned to care about the pixel boundaries in the first place.
Which is where Youtu-VL's vision as target comes in. It forces the model to stop skimming and actually read the image.
Exactly. They change the training objective. It's no longer just predicting text. It's modeling the joint probability of both the vision and the language sequences. The model is forced to be able to reconstruct the visual signals.
So the prompt is less, what is this? And more, reconstruct this image while you describe it.
That's the core idea. But that gets tricky architecturally. To speak an image, an LLM needs a vocabulary. You can't just auto-regressively output raw pixel values.
Right, you need to tokenize it somehow.
And this is where the Youtu-VL architecture gets really clever, especially with their Synergistic Vision Tokenizer.
I was looking at the diagram for this. The vision encoder is SIGLIP2, which is pretty standard high-performance stuff, but the tokenizer, that seems to be the special sauce.
It is. They build this unified vocabulary, V-unified they call it. And the tokenizer itself uses a learnable codebook to fuse high-level semantic concepts like what an object is with low-level geometric stuff, where it is, what it looks like. It uses cross-attention to spit out these discrete visual codes.
Okay, so it turns the image into a sequence of visual words that get added to the LMM's dictionary.
Yes. But here's the specific detail that I think makes this paper so elegant. Usually with a VQ-VAE or a tokenizer like this, you'd use it for both input and output. You discretize the image, feed the tokens in, and then ask the model to predict those same tokens out.
Sure, for consistency.
But Youtu-VL doesn't do that. On the input side, they skip the discrete tokenizer entirely. They use the continuous visual embedding straight from SIGLIP2.
Wait, why would they do that? If you have the tokens, why not use them for the input too?
Quantization error. It's a classic problem. When you force a rich, continuous image into a discrete codebook like forcing a specific shade of burnt orange into color token 405, you lose information. It's lossy.
Ah, I see. So by discretizing the input, you're already blinding the model a little bit before it even starts.
You are. So they feed the high-fidelity continuous analog signal in on the input side.
But they force the model to predict the discrete digital tokens as the target on the output side.
That's the move. It's incredibly clever. You get maximum perceptual quality coming in, but you enforce that strict, learnable, autoregressive structure coming out.
So that's the engine behind VLUAS.
That's the engine. Vision Language Unified Autoregressive Supervision.
Okay, so let's dig into that a bit more. It really boils down to the loss function, doesn't it?
It's a dual-stream supervision, really. You have your standard text loss, L-text, which is just next token prediction for words. But then you add L-image. Now, the model also has to predict the next visual token, VJ, given the context.
So it's reading a sentence like, the cat sat on the wall, and it expects the word mat. But at the same time, it's processing the visual stream, and it's also expecting visual token 402, which might represent the woven texture of that mat.
Precisely. And because it knows it's going to be graded on predicting that texture, it can't afford to throw that information away from its internal hidden states. It forces the whole representation to become incredibly rich.
There's a really striking image in the paper, figure 10. They show PCA visualizations, basically a map of the internal feature clusters for Youtu-VL versus Qwen 2.5 VL.
That figure is the smoking gun for VLUAS. I mean, Qwen is a fantastic model, but in their visualization, the visual features are a bit muddled. They overlap.
Right.
In the Youtu-VL plot, you see these distinct, sharp clusters. The features for different concepts are clearly separated, and that separation is a direct result of the model being forced to understand the fine-grained differences between visual concepts.
So we have a model that sees better because it has to speak vision, but the big claim is the generalist capability. And usually generalist means jack of all trades, master of none.
Right. Normally, if I want to do object detection drawing, a bounding box, a VLM might work. But if I want to do semantic segmentation coloring in every single pixel that belongs to the car class, I'm not using a standard transformer.
No, you're bolting on a SAM decoder or using a totally different architecture like a UNet. Because VLMs generate text, and a segmentation map isn't text. It's a dense grid of numbers.
Exactly. But Youtu-VL says, no thanks, I'll use the standard transformer for everything. They handle both sparse tasks like bounding boxes and dense tasks like segmentation without any extra architectural pieces.
How do they manage that? Those are fundamentally different types of output.
They split the capabilities into two prediction streams, but within the same model. Text-based prediction and dense prediction.
Okay, let's start with text-based. That's for localization tasks.
Correct. Things like object detection or visual grounding. For that, they use what's called an axis-specific vocabulary. It basically treats the coordinates of a bounding box as words. So the model literally outputs tokens like box by 100 y 200. This is becoming more common, but they do it really effectively.
Okay, that makes sense. But the dense prediction stream, that's the part that usually breaks a VLM. You can't output 1 million text tokens for 1 million pixels. It would take forever to generate one mask.
You've hit on the key bottleneck. Autoregressive generation is just too slow for pixels. So for dense prediction segmentation and depth estimation, they do something different. They stop treating the output as a sequence of words. They look at the model's raw logits directly.
Okay, let's unpack that. The logits are the raw probability scores the model calculates for every word in its dictionary before it makes a final choice.
Exactly. Before the model decides the next word is apple, it has a score for every single word. Youtu-VL takes those raw scores and maps them directly to pixel classes or depth bins. It turns the transformer's internal confidence scores into a visual map.
But there's a problem there, right? In text, you usually only want winner. The next word is apple, period. But in segmentation, a single pixel could be glass and window and transparent all at once, or you have huge class imbalance.
You do. Standard next token prediction, or NTP, just falls apart in that scenario. So the team developed a custom loss function they call NTPM, next token prediction for multi-label.
And what's the mechanism there? What makes it multi-label?
It changes how the model gets penalized. It uses robust negative sampling, so it looks at the hard negatives, the categories the model is most confused about, and it penalizes those mistakes more heavily. This allows the model to output a probability distribution across multiple labels for each pixel instead of just forcing a softmax to pick one winner.
So that lets them generate a dense mask directly from the transformer backbone.
It does, and from a deployment perspective, that's huge. If I'm an ML engineer, I don't need to load VLM weights, then separate SAM weights, then a depth model. It's all in the same set of parameters.
One model, one inference pipeline. You just change the question, you ask it, ask for a box, you get text coordinates, ask for a map.
You get a logit map. It simplifies the whole stack.
So let's talk about the training.
Sure.
Because teaching one model to do all of this at once seems like a recipe for, well, for catastrophic forgetting. How do they balance everything?
They lay out a pretty clear 4-stage process. Stages 1 and 2 are fairly standard, just building the language foundation. You want to make sure your LLM is a good LLM before you start messing with its visual system.
Right. Get the basics down. Then stage 3 is the multimodal foundation pre-training.
This is the key stage. This is where VLUAS kicks in and they turn on that L image loss. They're training on image caption pairs, but they're also mixing in vision-centric data.
Yeah.
And crucially, everything is trainable. The LLM, the vision encoder, the projector, it's all getting gradients.
And stage 4 is for fine-tuning.
Versatile task adaptation. This is where they apply that NTPM objective we talked about. But what's interesting is the data mix. They use about 30% vision-centric data-like segmentation maps, but they keep 30% general multimodal data in the mix.
Why do that? If you wanted to get good at segmentation, why not just hammer it with segmentation data?
Because you need to keep the generalist in generalist agent. If you only show it segmentation maps, it overfits. It forgets how to write a poem or answer a question. That 30% of general data acts as an anchor, holding it to its general purpose abilities.
Okay, so let's get to the receipts. They claim this one model can beat specialists. Does the data actually back that up?
It's surprisingly strong. They ran it on 75 different benchmarks. Let's start with semantic segmentation on ADE20K. That's a really tough benchmark, just a huge number of object classes.
Yeah, it's not just cat and dog. It's sconce, baseboard, wall.
Right. And Youtu-VL hit 54.2 MIOU. For context, another generalist model, GitT, scored 47.8. That's a really significant jump. It's competitive with, or even superior to, many specialized CLIP-based methods.
Okay, what about something harder for a generalist, like depth estimation?
They used the NYU V2 dataset. They got a delta 1 accuracy of 90.4%. Now, we have to be fair here. A state-of-the-art specialist model like UFO can hit 93.6%, so it's slightly behind the absolute best.
But UFO is a model designed only for that one task.
Exactly. UFO is bigger, has task-specific tuning, and it can't tell you what's in the image. Youtu-VL is doing this natively with no special heads. Being within 3% of a specialist while retaining full VLM capabilities is, well, it's impressive.
And object detection, how to do there?
On COCO, 47.1 MAP. That's right up there with specialized models, and it beats other generalist VLMs like Qwen3VL on many of the localization metrics.
I also saw they highlighted visual grounding on RefCoco, where you give it text of like, find the person in the blue shirt.
And they scored a 91.8% average, which beats Intern VL 3.5. This really proves that the vision as target approach helps the model understand spatial relationships. It knows where the pixels are because it was forced to reconstruct them.
There were some great qualitative examples in the paper, too. The one with the pugs with birthday cake really stood out.
Oh, yeah, that was a perfect real-world test. Messy photo, 2 pugs, a cake, cluttered background. And the model could not only describe the scene and count the candles, but also segment the pugs perfectly.
And the king crabs example.
That was a stress test, just a big pile of crab legs. For a normal VLM, that's just a texture of crab. Youtu-VL could pick out individual crabs and segment them leg by leg. That's the VLUAS fine-grained detail retention in action.
Okay, so this is a technical report, and to their credit, the authors are very honest about the limitations. We shouldn't pretend this is AGI, so what can it do well?
They highlighted 3 main things. First is a resolution bottleneck. Remember that input projector? They use a spatial merge to crunch down the visual tokens to keep things efficient.
Right, making the image smaller for the model.
Essentially, yes. Which means for extremely high precision tasks on a really high-res image, you can lose some granularity. You're not going to be segmenting a tiny screw in a 4K image if you've already downsampled it.
That makes sense.
Yeah.
The classic speed versus accuracy trade-off. What about geometry sensitivity?
This is a classic computer vision problem. Depth estimation usually relies on knowing the camera's sensor intrinsics, focal lengths, sensor size, that sort of thing. Since Youtu-VL is trained on this massive, diverse data set from the internet, it doesn't know the camera settings for any given photo.
So it might guess an object is 2 meters away when it's really 3, just because it can't tell if the photo was taken with a telephoto lens or the fisheye?
Exactly. It struggles with zero-shot robustness in unusual geometric environments. And the final one they mention is the cognitive gap.
The math and reasoning side of things.
Yeah. On benchmarks like MMMU, which tests complex mathematical reasoning and dense knowledge retrieval, it scores around 60. Now, that's good. It's a passing grade. But it's not beating the top-tier text specialist models that are purely optimized for that kind of reasoning.
It feels like a very deliberate trade-off. They prioritize perception seeing the world accurately over abstract calculation.
Which, if your goal is a visual agent, is probably the right trade-off. If you're building a robot to navigate a house, you need it to see the stairs much more than you need it to solve a calculus problem. You can always offload the calculus to a tool, but you can't offload the seeing.
That's a great point. So we're really seeing a move away from stacking specialist modules, a VLM plus a SAM plus a depth model, towards structural unification.
It's a much cleaner, more elegant approach. It's also much harder to train. You have to balance those loss functions perfectly, but Youtu-VL shows that it is possible.
It really raises a fascinating question for the future of AI. We've spent so much time treating images as just files we attach to a prompt. But if the model starts treating vision as a language, something to be spoken and predicted, token by token, does that bring us closer to agents that actually understand what it means to see?
I think it has to. When you make vision a target, you're telling the model that the visual world is just as important as the text describing it. It's not just input for a query, it's the reality the model needs to represent.
That's a fascinating thought to end on. If you want to dive into the code yourself, the team has released it. You can check the GitHub link in the description, and the model is up on Hugging Face under the Tencent collection.
Definitely worth a look for anyone interested in the nuts and bolts of VLUAS. It's a dense read, but a rewarding one.
Thanks for listening to this episode of AI Paper Podcasts. We'll catch you on the next deep dive.